Hello, boys and girls. It's Miss Salter. I hope you guys are doing good. Here's your lesson from last week. It's taken me a little while to kind of get this, but we are talking about gravity and friction and doing a little ramp experiment this week to see the effect of gravity on an object and also to see the effect of friction on an object. So your assignments this week, you should have watched the Brain Pop Gravity movie. And the username and password is right there up at the top. And please take the quiz when you're done, just for yourself for practicing. And there's a little game that you can play on that site called Balancing Act, which I thought that's kind of a fun one that tied into this. Today you are going to need your student activity packet, and we are on lesson number 4. So our learning target for today is I can explain what gravity and friction are and how they relate to each other. So keep that in mind, what gravity and friction are and how they relate to each other. So just a quick review, we are talking about Isaac Newton. He's a scientist from the 1600s. He came up with the 3 laws or rules to explain what forces are and how forces cause motion. Remember we talked about a force as a push or a pull. So his 3 laws, the first one is the law of inertia. Inertia is an object's resistance to change in motion. Law 1 states that objects need force to be moved or stopped. So you have to apply a force to move an object or apply a force to stop an object. Acceleration is the change of speed or direction of an object. So we're talking about acceleration with law number 2. It states that forces can slow down, speed up, or change direction of an object. And law number 3 states that if 2 objects come together, there will be a reaction to the action. This means that if one force acts, then the opposite force will push back. Remember, for every action, there's an equal and opposite reaction. All right, so first up, we are going to watch that Brain Pop video. If you've already seen it, great. You get to watch it one more time. If you haven't seen it, here is your chance.
Ow. Well, you didn't have to drop it on me. Dear Tim and Moby, how do we stick to Earth? Why don't we just fly off into space? From Chrissy. Sometimes I wish Moby would fly off into space. Yeah, whatever. Now, let's talk gravity. When Moby let go of that apple, it dropped towards Earth and hit me along the way. For thousands of years, philosophers wondered why this was so. Did Earth have some special quality that attracts all objects? It took a certified genius named Isaac Newton to figure out the answer. He reasoned that there was nothing uniquely attractive about our planet. Instead, a force called gravity made all objects behave this way. Everything in the universe has gravity. Earth, the sun, the moon, apples, even you. Newton proved that you could calculate gravity's pull with just 2 things, mass and distance. Massive objects exert a stronger pull than less massive objects. And objects that are far apart exert less gravitational pull on each other than objects that are closer together. This thinking satisfied scientists for more than 200 years. But then Albert Einstein came along and expanded on Newton's ideas. Good going, Einstein. Einstein wondered how gravity really works and why it depends on mass and distance. In his general theory of relativity, he showed that mass actually bends space. The more massive an object is, the more it bends space, and the greater its gravity. Yeah, it's hard to picture how space can bend, probably even for a brainiac like Einstein. New scientific theories often raise more questions than they answer, but you can think of it like this. If you put something massive on a trampoline, like a bowling ball, the surface sinks in a little. Put a smaller object nearby, like a marble, and it rolls toward the bowling ball. Kind of like how Earth orbits the sun. Well, it's not a perfect analogy. But don't worry, in real life, we won't fall into the sun. Back to our question, Earth's gravitational field pulls you toward the center of the planet. Since all objects possess a gravitational field, you're actually pulling back on Earth. But your pull is so much weaker, it doesn't make much difference. An object's mass isn't the same thing as its weight. Mass has to do with the amount of stuff in an object, and weight is the force exerted on an object's mass by gravity. On the moon, an apple weighs 1/6 as much as it does here. It's the same apple, but the moon's surface gravity is weaker because the moon is only 1/6 the size of Earth. Weaker surface gravity means that astronauts can jump 6 times as high on the moon as they can at home. The moon's gravity pulls at Earth, causing the ocean's tides. Earth's gravity keeps the moon orbiting around it, and the sun's gravity keeps us orbiting it. Gravity even holds planets and stars together. It's one of the most important forces in the universe, as far as we're concerned. Without it, we wouldn't even have a planet to stand on. Moby! Ah!
All right, well, I hope you guys enjoyed that. So what we're going to do is take a look at gravity and how it has an effect on an object by doing the let it roll experiment. So in your student packet, your student activity packet, you have this page. Go ahead and find it. And I'm going to be demonstrating this for you guys. Some of you guys told me you've already done it at home, which is great. This was optional. You did not have to do it. But let's go ahead and go through it together now and help us understand how the height of a ramp is going to affect how long it takes a little car to roll down the ramp. All right, boys and girls, here we are coming to you live from Miss Salter's house. I have a ramp set up here. I got a copy of my illustrated Harry Potter. I got a nice piece of wood here, and I got Mickey Mouse is going to help us here. And we are going to time how long it takes for him to travel down this ramp. And of course, we know that good science, you don't just try things one time. We want to try multiple times and get the average so we have some good results. So we're going to do it 3 times with 1 book, 3 times with 2 books, and 3 times with 3 books. And I'll share that data with you and we can go ahead and record that. All right, so here we go. First trial, ready, steady, go. All right, 2.15 seconds. For 2, we're starting from the same spot at the top of the ramp. Ready, ready, steady, go. Ooh, 3, here we go up at the top. Ready, steady, go. All right, 2.19 seconds. I think it may have given it a tiny push that second time. All right, so got another copy of Illustrated Harry Potter. Here we go. 2 books. I want to make sure my ramp is still at the same ending point, and so it's the same height on the books. So here we go. Trial number 2. Books. Trial number 1. Ready, steady, go. Oh, okay, that was much faster. 1.43 seconds. 2 books. Trial number 2. Ready, steady, go. Okay, 1.4 seconds. Again, this is trial number 3 with 2 books. Ready, steady, go. All right, ooh, 1.28 seconds. Girls, we have our 3rd book, another copy of the Illustrated Harry Potter, Prisoner of Azkaban. All right, we're gonna go 3 books high. And our ramp is nice and high now. Let's see how long this takes. Trial number 1. Ready, steady, go. Ooh, nice and fast. 0.98 seconds. All right, trial number 2. 0.95 seconds. And trial number 3. All right, 0.95 seconds as well. And we will come back together in just a second and average that out. But before we do that, what's one thing you noticed? Probably that the car was going faster the higher the ramp was. So why do you think that is? Take a second to think about that. Okay, boys and girls, so here is a chart that shows our data. For book 1, here's our trial 1, trial 2, trial 3 results, and over here is the average. So for 1 book, the average time it took for it to get all the way down that ramp that I had was 2.05 seconds. For 2 books, I averaged these numbers, and you guys remember the average is when you add all 3 numbers. So I added my trial 1, my trial 2, my trial 3, and then I divided by the number of numbers that I had. So I added those up and then divided by 3 because I had 3 trials. And the average for 2 books was 1.37 seconds. So that was shorter than the first one, or faster. And for 3 books, I did the same thing. I added 0.98, 0.95, 0.95, got a number, and then I divided that by 3. And that gave me an average of 0.96 seconds. So which ramp did the car travel fastest down? Yeah, the ramp with 3 books, right? So why did that happen? Why do you think that happened? What does gravity have to do with that? So our car, it was the same car every time. The only thing we changed, our only variable, was the height of the ramp. So the higher an object is, the more gravity can pull on it. So let's talk about what happened here. Why did it go faster when there was 3 books versus 1 book? You know, you've probably experienced something like that yourself. The higher something is, maybe the faster you're going to go. Maybe you're on a roller coaster. The higher up it goes, the faster you're going to roll down. That all has to do with gravity, that force that's pulling us all towards the earth. We have gravity pulling back, but the earth is much, much bigger than us. It has a greater force. But the force of gravity becomes greater as the height increases, or the higher up you go. So it's like the more gravity can pull you down, the higher you are. So we are going to get set up for our next experiment. Let's just review this real quick. Gravity. My goals today was to describe, like, what is gravity, and its relationship that it has with force. So we know that gravity is the natural force that pulls all objects towards the earth. And you should be pretty familiar with that. And there are 2 things that affect gravity. So the first one right here, you see a scale, that's one of your clues. The pull of gravity determines an object's weight. Gravity will have a greater pull on objects with greater mass. So the greater the mass of an object, the greater the pull on those objects will have a greater weight. So we've talked about that. Weight is gravity pulling down on us. Mass is the amount of stuff in an object. They talked about that in the brain pop video too with that apple. Mass is the amount of stuff that makes up that apple. So that's mass, but weight changes based on how much gravity is pulling on something. So the weight of that apple on Earth would be different than the weight of that apple on the moon, for example, because the moon is 1/6 the size of the Earth, so it has 1/6 the gravity. The other thing is, the farther you move an object away from the Earth, talking about out of the Earth's atmosphere, the force of gravity decreases. So at the end of this video, or the end of this lesson, I'm going to link another video that I just really, really liked that I think you guys will enjoy. It's optional to watch, but it talks about going from the Earth to the moon, getting there, breaking out of Earth's gravitational pull, then you're in space and you get pulled by the moon's gravity from there. So the further away from the Earth that you get, the force of gravity from the Earth is going to decrease. So the moon and me, on Earth, the pull of gravity is strong, pulling objects back to the Earth. And of course, every object has its own gravitational pull. So even us, we have a pull of gravity. But the Earth is much, much bigger than us. So of course, it has a really strong gravitational pull. So the Earth's gravity is strong, pulling objects back to Earth. But on the moon, there's very little gravity. An object would not weigh the same on the moon as it does on the Earth, which we just talked about. If you weighed 80 pounds here on Earth, you would weigh much less on the moon because there's not as much gravity pulling you down. And that makes sense. But of course, your mass would be the same. You know, the amount of stuff that makes you up would be the same, but your weight would be different based on the amount of gravity pulling you down. All right, so this is an optional second experiment. You're welcome to do this one at home. I'm not going to demonstrate this one, but if you're out there, you want to test some things, build your own ramp, make it as high as you want, as long as you want, and then you can try different surfaces and test the amount of friction. So a book without anything on it, book with sandpaper on it, book with felt, or any other types of surfaces that you have. And you can go ahead and test those out. All right, so just reviewing friction. We've talked about this before in class. We've talked about it throughout these lessons. Friction is the force that slows an object down. The more friction between two objects, the more work it takes to make motion. The less friction between two objects, the less work needed. And that makes sense, right? Like if you were trying to ride your bike on a smooth sidewalk or a smooth road, it's not going to be as much work as opposed to as if you started riding it through the grass or through, down a rocky trail or something. It's going to take more work. So friction is that force that's slowing objects down. So take a look right here. Sometimes there's just enough friction to help keep objects moving at just the right speed. For example, pavement has enough friction working against our feet so that we don't slip. Same thing with, the tread on our car tires and the road. There's just the perfect amount of friction. However, we have had some snowy, icy days, and ice has little to no friction, so it's hard to stay standing when you walk across it. Or maybe you've experienced that before yourself at the ice skating rink or something, or maybe your parents have been driving and the road has been icy up in the mountains or something. It's very slippery, so there's very little friction. Looking here at the soccer ball, when this ball is kicked over grass, it will start to slow down quickly because the grass has a lot of friction, as opposed to maybe if you kick that soccer ball over the ice, right? It's going to roll much further because there's less friction. So friction, just that force that's going to slow an object down. All right, that is the end of our lesson for today. So just make sure you filled out your paper with the ramp heights, and I'll go ahead and go back to that screen. So we're going to fill it in with the average. So the ramp height, one book, the average was 2.05 seconds, 2 books, 1.37 seconds, and 3 books, 0.96 seconds. So make sure you have that filled in. And down towards the bottom, it says, as the height of the books blank, gravity had a blank force on the car, making it go faster down the ramp. So what makes sense to fill in there? As the height of the books increased, gravity had a greater force on the car, making it go faster down the ramp. So make sure you have that filled in. That's that lesson 4 page there for you guys. And let's just wrap this up. So up next, lesson 5, I'm going to get that out to you guys pretty quick, is about potential and kinetic energy. You've maybe heard of those words before, maybe not. This is a little bit, can be kind of a simple concept, but it can also be a little tricky. So there's 2 videos on Brain Pop that I'd like you guys to take a look at, potential and kinetic energy. Take those quizzes just for your own practice. Down here at the bottom, student activity packet, look over lesson 5, just so you know what's going to be coming at you. And then optional, after we do this experiment with potential and kinetic energy, we're going to be building a pendulum. There was a packet in your science materials that had a reading passage called A Bundle of Energy. So you are welcome to read that. It is optional, but it's a good read if you want to take a look at that. And this is the end of our lesson. However, there was another YouTube video that I thought is like a compilation of 3 gravity videos. I thought it would be really fun. So I'm going to play those now, but they are totally optional. If you want to get a little more into gravity, this is kind of my new favorite YouTube station or YouTube channel right now. It's called Crash Course Kids. And I really like these, and I thought you guys would like them too. So,
must come down. A ball you throw in the air. An apple that drops from a tree. Even you when you're on a trampoline at someone's awesome birthday party. But why? My friend, let me introduce you to one of the most wonderful forces in the universe. It's one we're all experiencing right now without even trying. Fasten your seatbelts because we're going to explore the power of gravity. If I told you that you just won the lottery, what would you do? If you're like me, you jump up and down and scream. And after you were done freaking out and jumping in the air, you'd land on your feet, right? But why would you land back on the ground instead of just floating off into space? It's because of a little something we call gravity. Gravity is what pulls everything toward the ground, including you. Without the force of gravity, there would be no life on Earth. Air, water, animals, everything would fly off into space. There'd be no you, no me, no French fries, nada. Think of gravity like the invisible superglue that holds our massive world together. You can't see it, but it's always there. An English scientist named Isaac Newton was the first person to seriously study gravity over 300 years ago. There's a famous story about him that you might have heard. Supposedly, Sir Isaac was hanging out underneath an apple tree thinking, probably partly napping, when an apple fell from the tree and conked him on the head. That's when Sir Isaac had an aha moment. Why did the apple fall down to the ground and not up or sideways? So you realize that a special kind of force, which we now know as gravity, was acting on all of the objects on Earth, pulling them toward it. Once the apple became too heavy for its stem to hold it anymore, the gravitational pull of Earth brought the apple down onto Newton's noggin. Newton also realized it doesn't matter how heavy an object is either, whether you're holding an apple or a bowling ball or a feather. If you let go of it, that sucker's going down. We're gonna make a whole video about this later. Basically, he determined that what goes up must come down. Sir Isaac was a pretty smart dude. Okay, so you know that if you jump up, you'll eventually land back on the ground. And you know that an apple dropped down will land on the ground too. But what if you throw something in front of you, or to the left, or the right? To see how gravity will act, pick up the tennis ball or any small round object and hold it in your hand. Let's toss it in the air and watch it fall to the ground. No surprise here. Okay, now pick it up and hold it over your head. Let go and watch it fall once more. Again, not a shocker. Now throw it to your left, fall down, pitch it to the right, and watch it go down again. No matter where you throw the ball, it's going down. So we've determined that near the surface of the Earth, where we all are, gravity is the cause that produces the effect of all unsupported objects falling down. The ball will go up or to the left or to the right for a little bit, but eventually it's going to be pulled back down to the ground no matter what. Gravity's got a hold on, well, everything. So eventually everything that you can think of can be thrown up into the air and will come back down, even if you throw it to the left or the right or any other direction. That's gravity doing its thing. But when you really think about it, which way is down exactly? I mean, the Earth is round, and there are all kinds of things on what we think of as the bottom of the Earth. So how does gravity keep them from falling off? I know a penguin who can answer that question. So, you know that the Earth is round, and you know that gravity is the force that pulls objects down. But if the Earth is round, and there's stuff at the bottom of the Earth, say a penguin in Antarctica, why doesn't gravity pull the penguin down off of the Earth? I mean, does gravity really pull down? When we talk about gravity and we say things like up or down, we don't mean those things in the sense that you're used to. In this case, up just means away from the Earth, and down means toward it. So when you hear people say gravity pulls things down to Earth, they really mean that gravity pulls things toward the Earth. Now think of it this way. Gravity is the force of attraction between any two objects made of matter, right? Well, I have news for you. You're made of matter, and so is the Earth. That means you and the Earth have an attraction to each other. Aw, you guys. Anyway, the scientific argument for gravity is that any object that's on or close to Earth's surface and is made of less matter than Earth will be pulled in by our planet's stronger gravitational pull. Want to do a little demonstration? To show how Earth's gravity can pull an object, like the penguin we mentioned before, toward it, no matter where on Earth that penguin is, all you need is a tennis ball and a rubber band. Oh, and your index finger. Now, let's pretend the tennis ball is Earth, and the rubber band represents the force of gravity. That makes your finger our adorable little penguin, just chilling on the surface of the Earth. Now stretch the rubber band around your tennis ball Earth and stick your finger under the rubber band. Now try to lightly pull your finger away from the ball. The penguin is trying to jump off the Earth, even though penguins can't fly. What are you doing, penguin? But what happens? Not much. Your finger doesn't get far before the rubber band pulls it back toward the ball, right? And the effect is the same no matter where your finger penguin is on your Earth ball. Whether it's at the top or the side or on the very bottom, the same thing happens. The penguin is forced back to Earth no matter how hard it tries to jump off. So, what does this mean? It means that no matter where on Earth an object is, the planet's gravitational pull will draw the object toward it. And that's how you should think about gravity. It's the force that pulls things toward Earth. So basically, we have gravity to thank for the fact that penguins stick to the bottom of the Earth. And I, for one, am grateful. I like penguins. Interesting, huh? When we say that gravity pulls down, what we really mean is that it pulls everything towards the center of the Earth. But what if I want to take a break from the Earth? What if I'm an astronaut and I want to take a vacation on the moon? How can I possibly escape the gravity of the Earth? And if I can, what will happen as I get closer to the moon? I guess there's only one way to find out. You know how many people have actually been on the moon? 12. That's all. But one day, we may go back there. We have a lot more to learn about the moon and space in general. So someday, maybe in your lifetime, we'll send astronauts out there to study and explore. Do you want to be one of them? If you do, let me give you some helpful tips about a little thing called gravity, because you're going to need to know all about what gravity is and how it works if you're going to escape the pull of Earth and fly to the moon. Now, you already know that astronauts can leave the Earth, but it takes a lot of effort to boldly go where few have gone before. But once astronauts reach the speed called escape velocity, they're able to overcome the force of Earth's gravity and get into orbit around our planet, or head on over to the moon. So this brings up an interesting question. What happens when an object gets away from Earth's gravity, but close to the moon's gravity? You already know that gravity is the force that keeps us from flying off the surface of the Earth. And you know that gravity pulls things not down, but towards the Earth's center. You also know that gravity exists between any objects that have mass. And the greater an object's mass is, the greater the effect of its gravity, or pull, on other objects is. But there's something more. Remember Isaac Newton, the apple tree guy? He determined that the amount of gravitational force, or pull, between two objects also depends on how far apart they are. So the farther away something is from the Earth, the less it will feel the pull of Earth's gravity. And the closer it gets to the moon, the more it will feel the moon's gravity pulling on it. Let's do a little pretending to see what happens to something when it moves closer to an object that has a really large mass, and therefore a really strong pull of gravity. If you've ever made a wish on a shooting star, you've seen the effect of Earth's gravity pulling on an object. Shooting stars, which are actually meteors, occur when pieces of rock break off from a passing comet or asteroid and get too close to the Earth. For example, say this globe represents the Earth, and the marble represents a piece of space rock that's flying by. You can see that there's a huge difference in size between the two objects. And if we were to put them on a scale, we'd see that there's a big difference in their mass too. Our model Earth has a larger mass. If the space rock is far away from the Earth, then it can go on its merry way, since it won't be affected by the Earth's gravity. But if it gets too close, then it and the Earth engage in a bit of tug of war. Since both have gravity, they pull on one another. It's not much of a fight, though. The more massive Earth has a much larger gravitational pull, so the rock gets caught in Earth's gravity, and most of the time, it gives us a brilliant streak of light we call a meteor. But what does this mean for our space travelers? Well, when an astronaut ship takes off for the moon and moves away from the Earth, the farther from Earth it goes, the less it feels the pull of Earth's gravity. And as it gets closer to the moon, the spaceship begins to feel the tug of the moon's gravity more. So even though the moon has a smaller mass than the Earth and has less of a pull on the ship than the Earth does, once the ship gets closer to the moon than the Earth, the moon's gravity pulls the ship toward it. And then the astronauts can make a safe landing. So we can make the argument that two things affect the pull of gravity. First, the size of the object. Objects with a bigger mass have a stronger pull of gravity. And second, the distance between objects. The farther apart objects are, the weaker the pull of gravity between them. And the closer together they are, the stronger the pull of gravity. All of this means that when the day comes that you're flying a spaceship to the moon, you just have to escape Earth's gravity and then get close enough to the moon to enter its gravity. Remember that when you're grown up. And you're welcome. If you want to thank me, you could just name a crater or something after me when you get there. So here's what we know so far. Whether on Earth or in space, anything that has mass will exert the force of gravity. And on Earth, everything falls towards the middle of the Earth at the same rate. But hold up a sec. You've probably noticed that if you drop a piece of paper or a feather, it takes longer to reach the ground than something like a rock or a ball. So what's up with that? It's time to investigate. I don't care who you are. If you live anywhere near this planet, then you're no stranger to gravity, the force that affects every object on Earth and beyond. Because of gravity, whether you're an astronaut on the International Space Station or an ordinary, clumsy, earthbound human who happens to drop her books a lot, all things caught in our planet's gravity will, in some way, have the potential to fall to Earth. But objects fall differently, right? Like when I knock a piece of paper off my desk, it takes a lot longer to fall to the ground than if I knock a book off my desk. So what's up with that? Why do things seem to fall at different speeds on Earth? Well, we already know that all objects have mass. They have a certain amount of matter in them. And when gravity pulls on an object, it gives the object weight. Now, a long time ago, people used to think that heavier things fell faster than lighter things because that's what our senses told us. I mean, it certainly looks like the book falls faster than the piece of paper. And why would we expect anything else? That would be like dropping a hammer and a feather and expecting them to hit the ground at the same time. Except the thing I just said about the hammer and the feather, someone did actually try that, and they did both hit the ground at the same time. It just didn't happen on Earth. True story, when astronaut Dave Scott was on the moon in 1971, he did an experiment where he dropped a falcon feather and a hammer from the same height, and they hit the ground at the same time. Now, how can that be? If you drop a hammer and a feather on Earth, the feather would take a lot longer to reach the ground. So, what does the Earth have that the moon doesn't? For one thing, an atmosphere. The gases that make up Earth's atmosphere push against objects as they fall, and the push of the air against the falling object causes friction. We call that friction air resistance. So on Earth, the feather's flat, fluffy shape makes it run into more air resistance than the hammer does. This makes it fall more slowly than the hammer. But since the moon has almost no atmosphere, there's almost no air resistance. So the two objects fell at the same rate. So it seems to me that it's the resistance of air pushing against objects that really affects how fast objects fall. And that means that it's experiment time. But you don't have to go to the moon to do this, so don't pack your bags or anything. All you need are two pieces of paper that are the same size. Crumple one of the pieces into a tight ball and leave the other one smooth and flat. Now drop each piece of paper from the same height, let's say a meter, and then write down in a table how long it takes each piece to reach the ground. You'll see it takes the flat paper longer than the crumpled paper to hit the floor. This is evidence that an object's shape affects how fast it seems to fall to Earth, because the two pieces of paper are exactly the same. They have the same mass. But air resistance makes the flat paper seem to fall more slowly than the crumpled paper. So, based on the results of our experiment, we can say, at least here on Earth, objects appear to fall at different rates, not because they have different masses or weights, but because of air resistance, the force that the Earth's atmosphere has on objects as they fall. So there you have it. Gravity is the force that's exerted by everything that has mass, and it's felt by everything equally, even though falling objects on Earth might not always look like that's the case. I mean, if you don't believe me, you can go to the moon and do the old hammer and feather experiment for yourself. Or you can just trust me. If you enjoyed this, check out the rest of our channel and subscribe.